All right, welcome everyone. Thank you so much for showing up to our second ASPEN Net tutorial series on quantum networking. My name is Christopher Schwam and be moderating today. So this is the list of our upcoming tutorial schedule. And so you can get an idea of when our next tutorials will be. Roughly, they're going to be every 2 weeks at this same time. And today I'm really happy to introduce our speaker, who is Mike Mazurek. We'll be talking about path-entangled networks. Now, Mike did his PhD at the Institute for Quantum Computing in Waterloo, Canada. Then he moved to NIST, where he was a postdoctoral fellow, and now he's a research associate and has been leading a lot of our efforts here for actually modeling and trying to understand how to build an actual usable quantum network using photons. So I'm going to hand it over to Mike. Also, one more note. We encourage folks, if you have questions, feel free to either put them in the chat or just unmute yourself and ask. So as we go along. All right, Mike, take it away.
Okay, thanks, Krister. Thanks for the introduction, as Krister said. So today I'm going to talk about path-entangled quantum networks, and I just want to remind everyone that this virtual seminar series is part of our this NSF NQVL QSTD pilot program, which we're calling ASPEN Net, which stands for Attosecond Synchronized Photonic Entanglement Network. Hopefully by the end of this talk, all of those terms will be defined appropriately. That's my goal for the talk today. And there's a lot of players here. I'm not going to read all the words on this slide. But thanks to the NSF for this support. Okay, so this is my title slide. I'm going to talk about path-entangled quantum networks today. I'm going to define what I mean by that. And really, this talk's going to be about an architecture, a quantum networking architecture that we're pursuing. But before I want to say anything about quantum networking, I'm going to start with a very brief introduction to what entanglement is at a very high level. And so my kind of hand-wavy definition of what it means, or what quantum entanglement means, is it's a type of quantum state which can lead to quantum correlations between maybe two different particles or maybe just two different possible excitation modes that will persist even when you separate these particles by very large distances. And a little bit more precisely, maybe, still this is a hand-wavy definition, you could say that if you can imagine measuring both of the particles in an entangled state, for an example, if you implement the correct set of measurements, an entangled state can give measurement outcomes, outcome 1 and 2, which are going to be more correlated than or have stronger correlations, or they'll be equal to each other more often than is possible with any than classical physics can describe. So, okay, why is this useful? So one way in which this is useful is this has strong implications for secure communication. So this scenario, this little cartoon I drew, this is known as a Bell test because this experimental scenario was first introduced by John Bell. And the really important feature here is that if you can do an experiment that has no classical description, classical physics is a deterministic model. So if there's no classical physical description of the data that's measured in an experiment, and it turns out that this implies that there's some fundamental degree of randomness or unpredictability of the data. A different way to say that is that if data is fundamentally unpredictable, it's also fundamentally uncontrollable, which means that if there was some adversary trying to hack your experiment and fool you, they wouldn't be able to do it. Anyone who does that would not be able to create an experiment that has this correlation strength that's stronger than classical physics. So this is really important for a field within quantum information known as device-independent communication. And the basic idea here is that you can come up with cryptographic protocols which use the fundamental randomness that can be certified by measuring these stronger than classical correlations with an entangled state to do secure communication. So maybe one of the most well-known examples is this can be used to certify to produce quantum key distribution in a way that users will know that their quantum keys could not have been hacked or learned by any adversaries. So then that allows secure communication. Another application, which is actually from my group here at CU and at NIST, is the idea to generate to certify high quality, unpredictable random numbers with these Bell tests. And that has applications for lots of different cryptographic applications. So this kind of communication is one thing that entanglement is useful for. Another big topic is for distributed sensing. So distributed sensing on its own does not necessarily need to use entanglement. And the idea of a distributed sensor is you just have multiple sensors spread over a large area, which are maybe the goal is to do some sort of imaging or astronomy or measure RF fields. And if you distribute the sensors, that can lead to increases in sensitivity and or resolution. If these sensors can be networked, not with a classical network, but instead networked by entangled particles, the correlations in the entanglement, again, at a very hand-wavy level, can be there's this fundamental randomness in the entanglement, so that the measurements might be very noisy, but the noise can be very correlated between all the sensors. And that can lead to an overall increase, a quantum advantage in sensing. Okay, by taking advantage of the correlations in the noise. Often when people motivate quantum networks, the third category that folks talk about is distributed quantum computing. That is a very real application, which in the future, I think some quantum network will be useful for. That kind of category of applications isn't what our project is focused on, so I'm not going to talk about it today, other than just to mention it now that that's something else that entanglement is useful for, or distributed entanglement is useful for. So for these applications I talked about, so if you have entangled states, you can use them for quantum advantage and communication and or sensing. But to get a really useful advantage, you need to meet a lot of metrics simultaneously. So you need very high rates. These applications require measuring or consuming many entangled states every second. You need very high fidelity. So you need small errors in order to realize any quantum advantage. And also high efficiency. So high efficiency, like detection efficiency of the entanglement that you have, that does lead into having high rates. You want to measure most of the pairs you produce, but also for some applications, there's really a strict efficiency threshold. So for example, with device independent communication, it's only possible to measure these stronger than classical correlations in a secure way if the overall detection efficiency of the entanglement is greater than 2/3 or about 67%. So all of these things, these high rates, high fidelities, and high efficiencies have been demonstrated in labs many times. They've been distributed, or they've been demonstrated all together in many experiments in recent years. But the fourth thing that's required for the applications I talked about is distance. So if you're going to do communication, it's not really useful to do secure communication within one room or within one building. Typically, for most applications, you're going to want to be able to do that over a large distance. Also for distributed sensors, distributed's in the name of distributed sensing, so you need distance. And it's really difficult to marry this distance requirement to separate entanglement while maintaining these other three metrics at the same time. And one reason for that is it's just hard to transport entanglement across large distances. So just for a very simple example, imagine you have a pair of entangled photons and you want to just separate them by a large distance. Well, you might think that you can couple each of these photons into a fiber, send one off to the left and another off to the right, um, and then you have distributed entanglement. The problem with that is that, so optical fiber is probably maybe the most efficient way to transport light over large distances, but it's not efficient enough to go to super large distances. The loss in the fiber over, so this plot is showing the efficiency of going through fiber versus distance. And I'm assuming like the most efficient fiber that you can buy. I think it's 0.1 or 0.15 dB per kilometer to make this plot. And after only a few kilometers, the efficiency of just the transmission line drops below this 2/3 level. And things just scale exponentially poorly past there. So if you want to go, yeah, so this approach only gets you so far. Okay, and so this is where quantum networks come in. So my personal definition of a quantum network is in this first bullet point. It's a device that you can use that distributes entanglement over large distances. And then my kind of definition is that a useful quantum network is something that distributes entanglement over large distances while at the same time maintaining high rates, high fidelities, and high detection efficiencies. Those three the metrics we talked about on an earlier slide. Okay. So this brings me to the ASPEN Net project. I just want to say a little bit about what this is before I go on further. So our goal over the next 8 or so years, is to build this quantum network testbed, which we're calling ASPEN Net. And it's actually going to have 3 sites distributed across the US, in Boulder, Eugene, and Urbana-Champaign. Each of the sites will have varying numbers of physical nodes, and we'll have different kind of main focus areas, but our main the overall goal is to focus on this device-independent communication and sensing applications, these categories of applications. And we're really planning to build this as a service to the community. So there's going to be both remote access and physical user access to the network at all 3 sites. And so once this thing is built, maybe if someone has some algorithm they want to run or some cryptographic scheme they want to test, they can log in remotely and prepare all the states and define all the states and measurements they want to implement and test out that protocol. Or maybe somebody's building a widget that they think will be useful for a quantum network. Maybe it's a new source, a new type of detector. We'll also have physical user access, and we're going to welcome folks to come in, connect their equipment up to our network, and we'll help you test it. So ASPEN Net is based, it's an all optical networking architecture. The rest of my talk is going to be explaining what I mean by that. But the key features that I want to just say now, and I'll try to defend these claims through the rest of my talk, are that by the architecture that I'm going to talk about, it uses existing technologies, which is really important. I think it means that we have in my opinion, I think we have a good chance of success of building this thing and having it actually work, while maintaining the high rates, fidelities, and efficiencies that are required for the applications we're interested in. Okay, so for folks who are at Brian Smith's talk 1 month ago, the next 2 slides will look very similar to you, or very familiar to you. There's lots of approaches to quantum networking. Brian did a good job going over these. I don't have time to go over them today. But I'm going to talk about one approach, which our architecture is based off of, and it's this Dwan, Lukens, Zoller, or DLCZ scheme that was introduced in 2001. And okay, so For the rest of my talk, I'm going to start by going over in some detail how this scheme works, or how a version of this scheme works. And then after I've done that, I'm going to talk about our specific all-optical implementation of that scheme. And I'll talk about all the different components that we need to build to achieve that. Okay. So I'm going to start with a basic two-level system, some qubit. Maybe this is an ion, maybe it's an atom, maybe it's a cloud of atoms. I've intentionally drawn it as just this very arbitrary blob and labeling it as qubit. The important thing is it has two levels, a ground state and an excited state. And if you send an excitation laser in with photons of the right energy, you might bump the qubit from the ground state up to the excited state. So it can hold an excitation. And if this is the case, if you wait some amount of time, a photon might decay along some decay path. But when the qubit's excited, the initial state of the qubit, we write in this Brockett notation, this quantum notation, which just means that the qubit is in the excited state and the decay path has 0 photons in it. That's all that this means. And you can imagine sending a control pulse into an excited qubit, which will force the qubit from the excited state back down to the ground state. And when this happens, it has to emit a photon equal to the energy difference between these two states, which will go along the decay path. So in this case, the combined state of the qubit, the matter-based qubit, and the decay mode there are the qubits in the ground state, and there's 1 photon in the decay path. It gets a little bit more interesting if you consider sending in a weak control pulse. So there's only a 50% probability of the qubit decaying from the excited state down to the ground state. And so what happens here is you end up, this qubit decay path system ends up in the superposition of these two states. Either the qubit's excited and no photon has been emitted, or the qubit is in the ground state and a photon has been emitted. And this specific superposition here, this is the maximally entangled state of two particles. These are the types of states that that it's a quantum network's job to distribute. And so, states of this form are going to show up later in the talk, and every time you see it, just remember this means maximally entangled state, and that's good. That's what we want. Okay, so this is the initial step for the DLCZ scheme. And the second step is to take, so this is how you create entanglement between a qubit and a decay path. And the second step is to create entanglement between 2 qubits. And the way to do that in the DLCZ scheme is to start with 2 copies of this matter photon entangled system. I see someone's raised their hand. Feel free to just unmute and ask a question.
I unmuted myself. I'm Jim Eckstein at U of I. I just wanted to understand this thing you were discussing here about exciting the atom and then applying a control pulse. So when you excite it, are you putting in like a pi pulse that is guaranteed to bring it to the excited state?
Yeah. So I'm intentionally keeping these details very vague because there's lots of like different ways you could implement this. And actually what I'm talking about here isn't the exact system that DLCZ talked about in their original paper, but it's analogous. But yes, the idea is you start with, you need to have some control over this qubit. So there's a way to initialize it in either the ground state or the excited state with 100% probability.
Okay,
and I've just represented that as a laser or a pi pulse or whatever it is.
Yeah, okay. And then the control pulse would be what then in the language of pi pulses? Would that be like a pi over 2 pulse then?
I believe so. I'm not an expert in this area, but I think that's right.
All right. I'm just focusing on details, but thanks for clearing that up. Thanks.
Yeah, thanks for the question. Okay, so to entangle 2 matter-based qubits, the idea is to start with 2 of these matter photon path systems. And then what you do is you mix these 2 decay paths on a beam splitter and put 2 detectors at the end. And so what's happened in this situation is we've created a system on the left, which has a 50% chance of emitting a photon and then having it be detected, and also a system on the right, which also has independently a 50% chance of emitting a photon and having it be detected. And so there's 4 outcomes that can happen for this scheme. 2 of them lead to no entanglement happening, and 2 of them lead to entanglement being created. So I'm going to start with the 2 failure outcomes first. So the first outcome is that both qubits decay to the ground state and emit a photon, and then both of those photons are detected. So if this happens, you know that both qubits are left in the ground state. This is not an entangled state. We know that there was a failure. So this happens with 25% probability. Alternatively, both qubits could stay in the excited state. In this case, no photons are emitted and no photons are detected. We know both qubits are left in the excited state. And again, we still have no entanglement. This is a failure as well. The more interesting outcomes occur when only one photon is detected by one of these detectors. And so what happens here is, because of this beam splitter, we know one photon was detected. So that means that one qubit is excited and the other is in the ground state. But we don't know which one. Because of this beam splitter, we don't know which qubit this photon came from. It could have traveled this path, or it could have traveled that path. And so what happens is you're left in the superposition of the left qubit being in the ground state and the right being in the excited state, or vice versa. So ground excited plus excited ground. And if the other detector clicks and detects one photon and this detects 0 photons, then you end up with the same type of superposition. And if you go through the math, you'll see that there's a sign difference here in the superposition, which isn't really an important thing. Well, it's important to know about, but it can be corrected easily. So I've drawn these 2 phases, phi L and phi R, in these paths. And this is the phase that the photon accumulates as it travels from the qubit to the beam splitter. Or if it travels on either of these paths. And these phases show up as coefficients in the entangled state. And all I want to say about these 2 phases, this is the same state here again, is that if, say, for example, if this atom or this path length changes by something on the order of a wavelength of the photon, then this phase is going to flip the sign, maybe from a -1 to a +1 or something. And so it's really important in the DLCZ scheme that all of these paths are phase stabilized so that these phases can be controlled and known. And that's certainly a challenge for this DLCZ scheme. And it's something that has to be controlled. I'll talk later a little bit about how we plan to do that in our scheme. But this is maybe one of the larger challenges for this feature, this architecture. But I will also say that phase can be a feature. So if you have these entangled states that are very sensitive to small phase shifts, that could be really useful for something like a distributed quantum sensor. So if there's some phase shift on one sensor or on whatever is being measured by one sensor, then this sensitivity can be a feature if you're trying to measure something like phase. But it also has to be well controlled at the same time. Okay, so I just talked about how to make create entanglement between 2 qubits with some separation. And what I didn't mention is that the efficiency, so I have these probabilities. It looks like there's a 50% outcome of creating entanglement every time you try this, but this success probability actually depends on the efficiency of these paths and even just the probability of decaying into a path as well. And so it turns out things scale exponentially poorly with distance. So as you separate these 2 matter-based qubit systems, the loss or the efficiency from each qubit to the beam splitter is going to decrease exponentially, and the success probability is going to decrease exponentially as well. So for short distances, this can work well, but once you go to really long distances, the success rate is going to decrease exponentially, which is bad. So the final step of the DLCZ scheme is you start with lots of pairs of qubits that you try to entangle, matter-based qubits, and then you just try each trial. So maybe the first trial you try to entangle each of these 4 pairs, and one of them succeeds, and that's great. 3 of them fail, so you just try again and keep trying again until they've all succeeded. Um, an important thing here is that whatever matter-based system is in here, it has to have a long-lived lifetime. Like your qubit has to have some very low probability of decaying in time in order for this to work. And so that's why we call these qubits as matter-based quantum memories. They need to be quantum memories in order for them to work well. And then once you have entanglement distributed in all of the pairs across the chain, then if it's set up in a way where pairs of qubits are close to each other, you can think of this as like maybe these are inside like a 2-qubit quantum computer, for example. It's 2 qubits that you need to have very, very good control over in terms of doing measurements and local operations on them. Then, so just like we can entangle 2 qubits by starting with an entangled state here and an entangled state here, and then doing a measurement in the middle, which will leave these 2 matter-based qubits entangled. If we do the right type of measurement here, which is called a Bell state measurement on these 2 qubits, it will leave these 2 qubits entangled. And because this is a matter-based thing, and this, as I said, this kind of idealized 2-qubit quantum computer, in principle, this measurement can be done with unity success probability, or very high success probability in practice. So you can just implement all of these in a row. There's a very high chance that they're all going to work. And this is how you end up with entanglement distributed across both ends of the network. So this is the DLCZ scheme. There are some recent state-of-the-art demonstrations just from within the last year from a group in Delft and in John Wei Pan's group. And they've demonstrated this scheme kind of in the way that I've just described it for few node networks over distances of about 10-ish kilometers, I want to say. I don't remember the exact numbers, but like something like that. So the Delft group uses nitrogen vacancy centers as their 2-level system. John Wei Pan's group uses a clouds of rubidium vapor as their 2-level system. So the pros of these demonstrations is that the lifetimes of their memories at the NV centers, or these rubidium clouds, are relatively long. I think on the order of a few milliseconds, which is good. But the challenges are that the successful entanglement generation rates that have been demonstrated are in the order of 1 to 2 successfully distributed entangled states per second. And the state fidelities are also relatively low. They're like 60 to 70%. They're just above the threshold of what's useful to see any quantum advantage. But when the state fidelities are low, you need exponentially more copies of those states to see a useful advantage. So higher state fidelities and higher rates are definitely needed. Okay, so our alternative is to use an all-optical approach, and our encoding is this thing, which is a path-entangled single photon. So the idea is that you start with a single photon, send it on a beam splitter. It's either going to be reflected, and the photon will be in mode 1, and not in mode 2, or it'll be transmitted, and the photon will be in mode 2 and not in mode 1. And we represent that with this state here. So there's 1 photon on the left and none on the right, or 0 photons on the left and 1 on the right. And this is the maximally entangled state. And it's, relatively easy to make. I'll talk a lot more about this later, but I'll just say now that if you're using something like a 100 megahertz repetition rate laser, you get to attempt to make a single photon 100 million times per second, and then every time you make one, it's going to deterministically be entangled. So the rates of generating entanglement can be orders of magnitude higher than what you get with these systems. Because of the long memory lifetimes, that memory lifetimes kind of correlated with the bandwidth, or the bandwidth of the excitation. So they have very narrow bandwidths, which means very long coherence times, which limits the rate at which you can, the trial rate of any experiment here. So with an all optical approach, the trial rate can be much higher than with these matter-based approaches. And this is analogous, this 1001 state is analogous to the excited 0 plus ground 1 state. So here there's one excitation, which is just entangled between two modes, two paths. Whereas with the DLCCs, the matter-based scheme I talked about before, it's one excitation, which is entangled between the qubit and the decay path. Okay, and so you can use these path-entangled states to violate a Bell inequality, to measure these stronger than classical correlations. And the way that you do that is by interfering each mode with a very weak laser pulse and detecting in a homodyne or homodyne style measurement. This was first discussed in around 1990, and these are the two earliest papers I could find discussing this idea. And this is great because it means that these states can be used for device independent communication. So that's good. That's one of our application areas. And also, these states are great for quantum sensing. So one example here is to do distributed interferometric imaging by sending connecting two telescopes, which are trying to image maybe a star or some object with a path-entangled state. So this is like this picture is a simple example of a networked distributed quantum sensor. Okay. So entanglement swapping with this path encoding works in the very analogous way, or the exact same way as for the matter photon system. So, and I want to say that this all optical path entangled, single photon path entangled swapping, or a version of this has been demonstrated before by Rob Thew and members of his group in a very nice experiment. And in this paper, they were also able to implement these interferometric measurements to get experimental evidence of entanglement, or heralded distributed entanglement. Okay, so I think it's, well, I'm just going to recap how entanglement swapping works with the path entangled states. So you start with a single photon on the left and right side of the experiment. These beam splitters create two path entangled states between these two pairs of modes. And so we know that we started with two photons, and let's just say we detected one. Then we know there's one photon left in the system somewhere. And so, but again, we don't know which side of the experiment this detected photon came from. So we end up with the remaining photon is in a superposition of the left mode and the right mode. And this creates the path entangled, a distributed path entangled state that we're looking for. So I've been sweeping a big detail under the rug when I've been talking about swapping, and which is that my description here has been assuming that there's 100% transmission efficiency everywhere in the experiment and 100% detection efficiency. That's not really a good assumption. That's non-physical, and if we had those links, we wouldn't need a quantum network because it would be easy to just distribute entangled states of light over whatever distance we wanted. So there's always some loss. So here I've represented loss in these transmission channels as maybe you couple into some long fiber There's a lot of loss in the fiber, and there's loss coupling in and out. The detectors are inefficient as well. And so when there's loss, what happens is if you detect one photon, well, we know that that one photon came from either the left or the right side. And we know there's one other photon somewhere in the system, but we don't actually know where it is. It could be in a superposition between the left and right modes paths here, but it also could have just gotten lost somewhere in fiber. So actually, when you detect one photon, you actually end up with a mixture of the entangled state that you wanted, but then there's this error term, which is that maybe the other photon was just lost. And the way that you deal with this is by just changing the initial state. So you reduce the probability of a photon. Instead of having a 50% probability of the photon being transmitted or reflected at each beam splitter, you change this beam splitter so there's actually a very low probability of the photon going into the middle and a much higher probability of it going this way. So now when you detect one photon, it turns out that it's more likely that the other photon is in the superposition versus having gone into fiber somewhere and being lost somewhere else in the experiment. So the trade-off here is that you can lower the overall success rate of the entanglement distribution to reduce the error in the final state that you end up with. So I have a simple plot of this here on a log-log scale. So this y-axis is the success probability of distributing an entanglement, given that you start with two photons, as a function of the efficiency in these transmission lines, including the detector efficiency. And you can see that as the efficiency decreases, the success rate also decreases. And you can choose different levels of error. Different applications will have different amounts of errors that are desirable or acceptable. And as you decrease the amount of error, acceptable error, the success rate has to decrease proportionally. But this is all to say that it's still possible to distribute high quality entanglement over very lossy channels in this all optical way. I talked a little bit before about synchronization. There's phases in these transmission lines. In our case, we're planning to use 1550 nanometer light to control these phases to within our metric of 1/100th of a wavelength. This corresponds to synchronizing the lengths of these two paths, or the propagation time of these two paths to within 5 attoseconds. This is why we're calling ASPEN Net. This is where the attosecond synchronization from component of ASPEN Net comes from. And we'll talk. There's an upcoming talk from Nick Nardelli, one of our colleagues here at NIST, who's working on this and has some very promising results showing that we should be able to do this in a quantum compatible way. Okay, so stay tuned for that. I'm running a little bit behind on time, so I think I'm going to skip. I'm going to try and go through some of these next slides a little quickly. I haven't talked yet about how we're going to produce these single photons. And our idea is to use spontaneous parametric down conversion, which is a process which produces pairs of photons. So if you can send some pump laser into some nonlinear crystal, and some probability, some typically very small probability, any one of the photons in the pump laser can split or down convert into a pair of lower energy photons into what we call a signal mode and an idler mode. This process has to satisfy momentum and energy conservation, and so which are represented by these two equations here. And so typically what comes out of the crystal is this mess of light coming out in all these modes, but you can select just a single pair of modes by coupling into single mode fiber. A single pair of spatial momentum modes. And okay, so you can set up an experiment like this. It's because photons are produced in pairs and because of the momentum and energy conservation, we know that if we put a detector here at the end of this fiber, if we detect a photon here, we know that there will be a partner photon in this other fiber. And then this partner photon is our single photon, which will then send to a beam splitter to create a path-entangled state. So this is the way to create single photons, not necessarily on demand, but in a way that it's heralded, so we know when it succeeds. So most of the time in typical SPD experiments, usually you send a laser pulse into this crystal and no photons are produced, no pairs are produced. Sometimes you get one pair, and then we can detect it with this detector, and less often you can get 2 or more pairs being produced at the same time. And so these detectors, in order for this scheme to work really well, we need these detectors to be very efficient. Ideally, they would have some limited number discrimination, so it can tell the difference between 0 photons, 1 photon, and 2 or more photons sending them, and then we can only use the trials in which exactly 1 photon was detected, because that means we have exactly 1 photon in this other fiber. And we want them to be fast. Marty Stevens is going to talk about kind of all the detector requirements we'll need for all the aspects of this network in an upcoming seminar. So stay tuned for that as well. There's a couple of really important metrics for the sources that we need. So we want the probability to get this high efficiency. We want to know with very high certainty that if we detect a photon here, that its partner makes it into this fiber here. So things need to be engineered and aligned very carefully to ensure that happens. We want that probability of this heralded coupling efficiency. So the probability that if we detect a photon here, we have one in this fiber. We want that to be above 90% or probably even higher. And that's something that our group does. So I'm going to take this opportunity to advertise a recent paper from our group where we had a very high heralded coupling efficiency. Okay, and then also another really important thing is that we need to be able to make many identical copies of these sources because there's going to be many copies in the network and we'll be interfering photons from different sources together. And so these sources need to have a high degree of indistinguishability. So they can interfere with very high visibility. I don't have time to explain exactly what I mean by that, but this has been demonstrated fairly recently by Alessandro Fedrizzi and his group. And there's a future seminar which will be given by Christer Scham coming up on May 1st, and he's going to talk more about sources and how to build these things. Okay, so stay tuned for that one as well. Okay, so these sources need to be synchronized. They're probabilistic. Every pump photon that goes into this crystal has just some small chance of being down converted. And so if we have 2 sources and we're trying to implement entanglement, interfere them to implement entanglement swapping, we need those photons to be synced up in time. And if you just start with 2 kind of free running sources, there's no guarantee with in any input pump laser pulse that both of these sources will produce a pair at the same time. And so one option is just to wait a really long time until they both happen to prepare one at the same time. Or another option is to use a quantum memory and a feed forward signal, so you can send in a bunch of pulses, wait until one of them creates a pair. And so we wait until you get this heralded single photon, store that photon in memory until the other source also has one, and then release both photons at the same time. So normally when I think of a quantum memory, the first thing that jumps to mind is I think of light being absorbed by some atom or some matter-based system, which has some really long lifetime. And that's not what we're going to be using in ASPEN Net. And the reason is because that those memories are very inefficient. And I've already said we need very high efficiency. So we need the probability of coupling into and out of the quantum memory to be, extremely high, like again, above 95% or something like that. And that's just not possible right now with matter-based quantum memories. So instead, we're going to use these simple all optical variable delay lines as quantum memories. Okay, so what I've drawn here is a photon going into a system. It's specifically horizontally polarized photon, which interacts with these two square things, or polarizing beam splitters. And the way I've drawn it is a polarizing beam splitter will transmit a horizontally polarized light with 100% efficiency. So if you send a horizontally polarized photon in, it's just going to go through these two beam splitters. And we also have this control. I've drawn this Pockle cell, which is an electro-optic cell which can be used to flip polarization, controlled by applying some voltage from horizontal to vertical. And so if this Pockle cell is on, the horizontally polarized light will be flipped to vertical, in which case it will be reflected by the polarizing beam splitters with 100% certainty. And we'll take this longer path through the system. So it will be delayed by some value of delta t. So you can imagine stacking a bunch of these things up. So in this example, I have 3. So there's one delay line, which gives a delay of delta t, one which gives a delay of twice that, and one which gives 4 times the delay. And with the right number of Pockle cells, you can independently choose for each of these 3 paths, which, if it's going to take the short or the long. So there's 2 to the 3 equals 8 different combinations of short and long paths through this system. Which gives you 8 total different delays that can be chosen. So the good things about this type of memory is they can be very efficient and they can operate very quickly. These Pockle cells can be switched on like the nanosecond timescale. This type of memory is not suitable for super long storage times, so more than tens of microseconds, for example, because they're just not efficient enough. But that's okay for our purposes. And these all-optical quantum memories have been built and really pioneered by Paul Kwiat and his group. And there's going to be a future seminar about those coming up in a couple weeks. So again, stay tuned for the details of that as well. Okay, I'm almost done. I'm wrapping up here. So the final thing is to put all these components together. So we talked about sources, these SPDC-based sources, where when you detect one photon in the pair, you know the other one's there. That gives you this heralded photon. That can be stored in some all-optical quantum memory. And these 2 memories can be synchronized so that they, with high probability, will both emit photons at the same time. They can be sent through fiber to this beam splitter and pair of detectors. And this is how you do, this is a simple network link for an all-optical architecture. And when this measurement in the middle succeeds, it will lead to entanglement between this left path and this right path. And so this is how we can distribute entanglement, high fidelity entanglement across lossy channels. Again, we can't just arbitrarily separate these 2 sources by as far as we want, because rates scale exponentially poorly with distance in this case, or exponentially poorly with loss, really, even distance and loss scale in that way. So you can use the same kind of trick as in my earlier slides from DLCZ. You could try doubling this up. So split this into 2 halves. So now I've drawn 4 sources, and on the left there's 2 sources, and you do swapping, and on the right there's 2 sources, and you do swapping. And there's an important thing here. So this source in the middle, one mode goes to the first swapping stage, and another mode just goes into this really long delay line, and then another quantum memory where it waits for a signal to come and say that the swap succeeded, so that you know that now the photon in this path is entangled with the photon in that path. And the same thing happens on the right side. And these delay lines have to be pretty long, because it takes a long time for light to go along this fiber, have the Bell measurement either succeed or fail, and then send this signal back here. So the length of this fiber is going to be on the order of, or it's always actually going to be longer than the length of this transmission line here from the source to the first Bell state measurement. But then once these both succeed, then we can try a swap in the middle. And if that succeeds, that leads to entanglement between the far left and the far right side of this network. You can double this up again and have 3 swapping stages. The feed forward is a lot more complicated. I'm not going to spend any time on this picture other than to say that it's possible to do. And so now we're finally ready to ask the question of how well can this all optical ASPEN Net architecture work? So I'm going to start with a simple example. Let's say that we have two labs, A and B, and the goal is to share entanglement between them. They're connected by a long, very efficient 0.15 dB per kilometer loss, a very efficient fiber. And the question is, what's the most efficient way to share high fidelity entanglement between these two nodes? So to answer this question, I'm going to assume that we can access the fiber anywhere along its length to add either a quantum memory or a swapping stage or whatever. And so then you can optimize over the number of swapping stages and also the initial states sources. Okay, so this is an optimization problem that needs to be solved. I've solved it. The results are going to be on the next slide, but I want to say that take the numbers that I have on the next slide with a grain of salt. I have a lot of very optimistic parameters. I think most of them are relatively realistic. The ones in black certainly are, but they are optimistic. And I'm basically assuming it's kind of the ideal case in terms of rates, efficiencies, everything that I think is possible today. There's a couple parameters that I put in orange here because I want to highlight that they're maybe a little bit less realistic. And I think if I relax those assumptions, the numbers that I'm going to show will certainly get worse. So I'm assuming that we're perfectly able to filter out any double pair events from our down conversion sources, and also that all the sources are perfectly indistinguishable. So there's 100% visibility. And then the final one is that I'm assuming detectors with no background counts. So every time we get a click, it's really from a photon that was created by one of our sources. So with all these caveats in mind, here's the result. So if you have a long separation in fiber over this very efficient fiber, so I'm plotting here the entanglement distribution rate on a log scale as a function of total network length. I'm assuming a 100 megahertz laser rep rate or trial rate of the network. And in blue, I'm plotting the rates that you get with just a single swap and enforcing this 99% fidelity of the final distributed entanglement. And you can see this characteristic exponential scaling with loss. And it actually turns out that going to 2 or 3 stages for this set of parameters isn't useful. And that might seem surprising, but the reason for it is that there's these transmission lines and these delay lines. And in this plot that I just showed, I'm assuming that the efficiency of the transmission lines is equal to the efficiency of the delay lines. So it actually, in this case, it doesn't make sense to add a second stage of swapping because it ends up adding a lot of extra loss in the network and overall is just going to decrease the rates. But I don't think it's very realistic so this 0.15 decibel per kilometer loss in fiber, this is kind of the best fiber that you can buy today. And for like a real world deployed quantum network, it's not realistic to assume that the transmission lines are going to have that are going to be super high efficient. There's going to be bends and splices and lots of stuff going on. The delay lines, that's just going to be a spool of fiber in a lab. So you can spend the money, buy an expensive piece of low loss fiber and achieve that. So these cannot be low loss, but the long links cannot. So if I just change this one parameter, I assume that the transmission lines are 3 times as lossy. So this is about 90% efficiency per kilometer. Then you can see, again, so the overall entanglement distribution rates decrease, but and there's some, for long enough networks, there's some point where using 2 stages is optimal, and we're in 3, and also we're using 3 stages is optimal. over just one. So I want to point out here that the rates are still pretty good. So again, with all these optimistic parameters, we're still getting 1,000 entangled pairs per second over 100 kilometers of distance. And that's way better than one, which is what the state-of-the-art demonstrations have shown. So I think there's really high promise for this all-optical approach to get really high entanglement distribution rates. And this is also with these really high state fidelities compared to the 60 or 70% of the state-of-the-art demonstrations. You can also model what if the fiber is not in a straight line. This is maybe for time, I'm going to skip this slide and just go to the end. So hopefully, thanks everyone for your attention. Hopefully I've convinced you that there's some promise to this all optical quantum networking architecture. I think we can simultaneously get high rates, efficiencies, fidelities, and pretty decent distances, definitely city-sized, if not maybe further in some idealized situations. We're planning to build these ASPEN Net testbeds. They're going to distribute entangled states, which I think are ideal for quantum communication and sensing applications. And I think we have a chance of doing it because all of the basic technological components that we need have been demonstrated already. I don't think that this all optical approach is ever going to be able to be used to share entanglement between, say, like LA and New York. That's just too big of a distance and it's not going to work. For larger distances, you can imagine some future quantum internet where there's quantum computers that are entangled all across the country or the continent. Those are going to need to use some hybrid approach. But for the kind of the smaller, some hybrid approach which has these matter-based, longer-lived memories in them. But for the kind of the last mile networking applications, or for these initial test beds, this all optical approach, I really think is the way to go, and we're really excited to be working on this and trying to build it. So thanks everyone. I'm just going to leave up this last slide advertising a town hall that we're holding in San Francisco in June. Scan the QR code for more information if you're interested. Thanks.
All right, thanks, Mike. So we had a question from Rob who said, is there a plan to talk on how you measure the entanglement?
So sorry, is there a plan? Is the question, is there a planned seminar about measuring the entanglement?
Yes, that's the question.
Yes. Okay. So no, I don't believe we have one, at least not in our current plan, not in our current schedule. That's definitely a topic. If this seminar series continues to be well attended and there's interest from folks, I think that's a great idea for a topic. Maybe you would be a good guest speaker for that, or maybe you
That's
just want to come and listen. Yeah, it's certainly an interesting topic, and it's something we're thinking about, and it's not well, we have to work out the best way to do it still. We have different ideas, but our idea is to use these displacement style measurements. I drew a cartoon of them on a slide earlier where you interfere a very weak laser with each mode of the path entangled state.
Okay. We'll see how we go.
Yeah.
Sorry, we have a question from Boris. Do you want to unmute and ask your question, Boris?
No, I'm just, I was just wondering, I mean, certainly it looks like one stage of entanglement swapping buys you a lot, because you can really go to this long distance. But I'm just wondering
Yeah.
if, wouldn't it be sort of simpler to, convince people to lay ultra low loss fiber in these dedicated quantum networks, and then just concentrate on having like lots of these really high quality entanglement swapping stages with one pair of memories? 'Cause it just seems like it would be a better use of resources.
So I certainly agree. If we had access to this ultra low loss fiber, that would be fantastic. And yeah, there would be very few situations where you need more than one stage of entanglement swapping, and it just makes everything way simpler to implement. You said that wouldn't it be easier to convince people to lay this low loss fiber? That I don't know.
I mean, they do.
it's not.
They already use it. They already use it in transatlantic, underwater. So, I mean, if we're convincing governments to build a quantum network, that might actually be the way to go.
Yeah, it might be. I think Krister might have more insight on this.
Yeah, so one of the things where it gets a little more complicated is if you have a straight line with the optimal geometry and you can put your repeater like exactly in the middle of the road where you need it to go, then yes, this would be a great way to do it. But in reality, like if you've got any kind of like more realistic loss or the fiber path isn't straight line, so maybe it's low loss fiber, but it takes a meandering path to get there, so it has effectively more loss, then you end up with a very different regime. And there's some other parameters like run memories and stuff where this kind of shifts around. And I think if you start going to two-dimensional networks, we haven't done the model for it. But in 2D networks, it gets, I think, even more complicated.
Yeah, that makes sense for sure. Yeah. Thanks a lot.
Sherman, do you want to unmute and ask your question? Oh, okay. So the question is, would there be a talk on interferometric measurements and characterization of entanglement?
Okay. Yeah, I think that's a very similar question to Rob's question. Will there be a talk on how we plan to do the measurements? Well, we've had 2 requests for it now, so I think maybe we should say yes, there will be a talk. We'll put that on our topics list.
And part of that will also be about how to do at least some of the stability that's needed for the measurements. We'll be coming up with Nick Nardelli's talk on stabilization. So yeah, we'll definitely dedicate a session to do this. It seems like a popular request. Any other questions from folks? Okay, well, I think we're over time, so we'll end it there. This recording will be made available and saved for folks, and we'll have it up on our website hopefully soon. We're still working out some logistical details with setting up the YouTube account. But we thank you everybody for tuning in and for the lively discussion in the chat, and we hope to see you all in 2 weeks. So thank you so much.
Okay. Thanks, everybody.